My name is Noureddin Menad. I'm expert scientist working at BRGM, National Geological Survey in France. Today, I would like to talk about the recovery of valuable metals from EAF slag by microwave-assisted leaching. This work was carried out at BRGM as part of the French IPAS project, Phytomanagement Approaches for Steel Slag Management, founded by the French National Agency. Currently, we are noticing the depletion of natural resources in the world, and there is a strong demand for primary resources of metals used in high technology, while these metals become depleted in the future. One of the solutions to solve this problem is to get these metals from secondary resources such as metallurgical byproducts containing metals, like chromium, vanadium, molybdenum in our case. To recover these metals, there is a need for more efficient technology in order to minimize the expenses, the environmental impacts, and to meet the increasing demand of these metals for the high tech. Slag could be a very good secondary resource as they contain high content of different metals. Therefore, they should be viewed as a resource, not as a waste. The challenge is to be able to selectively recover valuable metals, and this by knowing their physico-chemical characteristics. For our work, a representative sample of slag generated from EAF, electric arc furnace supplied by the French steel industry, was characterized and processed in order to recover these metals and to valorize the residues obtained. The objective of this project is to develop a methodology to recover strategic metals and valuable metals contained in EAF slag by using innovative alkaline leaching, conventional and microwave roasting, followed by leaching of these metals. To classify its efficiency compared to the conventional roasting process, and to valorize the residues obtained from treated slag. For the material, as I said, the investigated samples were provided by the French steel industry and generated from EAF process. These slag were landfilled for several years because there was no technology available to valorize them. According to the new legislations, these slag must be treated and valorized. For now, the French industry has removed the iron scrap by primary magnetic separation to recover them in the same furnace and to solve the treated slag for further processing. The methodology applied in this project shown is this flow sheet. After sampling and grinding, the iron scrap were removed by dry, low-intensity magnetic separation. The slag free of iron scrap were again crushed and grinded to obtain the size fraction of 125 micrometer. Different alkaline reagents such as sodium and potassium hydroxide and carbonates were tested for leaching the metals contained. Co-grinding of the slag with reagents for 1 to 2 hours was applied in order to obtain a homogeneous mixture and the reactivity of reagents. The mixture was then roasted in microwave under different parameters like power, residence time, and humidity. The dynamic leaching in water was carried out on the roasted sample. After filtration, the solution and the residues obtained were characterized by conventional analytical techniques. LDH layered double hydroxide were tested to recover the dissolved metals. After filtration, the solution was analyzed to calculate the recovery rate of each metals. For the results, the material characterization, then the representative sample of the slag was characterized, and the following table shows the chemical composition of the investigated sample of slag. It shows that this slag contained 3.4% of chromium, 154 ppm molybdenum, more than 1000 ppm for vanadium, 48% of iron oxide, and more than 5% of manganese oxide. As shown by photos taken from the scanning electron microscopes, this slag is very heterogeneous. Point of view, morphological aspects, and also chemical composition. The X-ray diffraction reveals the following crystalline phases, such as larnite, magnetite, cerebrodowski, hematite, burstite, chromite, magnetite, and quartz. The Morse-Bohr spectroscopy gives different valences of iron, and it shows that the slag consists of more than 50% of paramagnetic compounds. Here, the primary tests were carried out on the microwave roasting of different mixture of slag with different reagents for 10 minutes. The figure shows the best results obtained. It shows the leaching rate of this mixture as function of the roasting temperature. It found that sodium and potassium carbonate do not react with slag. The temperature of the microwave is low, and that potassium hydroxide and carbonate have good reactivity with the slag by increasing the temperature, and the leaching rates are the highest. The microwave roasting tests were performed on wet and dry mixture of slag with reagent. We would like to show the humidity effect. The figure summarizes the results obtained, and it shows the leaching rate of these metals for different mixture roasting in dry and wet routes. It can be seen that the highest leaching rate of chromium is obtained for the mixture slag with potassium hydroxide with potassium carbonates. This slag summarizes different results obtained from microwave roasting assisted leaching chromium, vanadium, molybdenum in different microwave roasting conditions. The figures shows the evolution of leaching rates of the desired metals as function of microwave residence time for 1, 1, 2, and 1, 4 kilowatts. It is noted that the leaching rates of chromium and molybdenum are close to 100% for 15 minutes of roasting of the slag with potassium hydroxide. The same results are obtained for 1.2, 1.4 kilowatts. The leaching rates of vanadium are low for all conditions. We can see that the leaching rates of these metals are low for the mixture slag with potassium carbonate, and it seems that this reagent inhibits this reactivity of potassium hydroxide with slag see the results shown in the right side. This slide summarizes, gives the table which summarizes the results obtained from conventional and microwave roasting assisted leaching. It can be seen that the best results were obtained when the mixture of slag with alkaline reagents are roasted in microwave during 15 minutes. However, it takes 1 to 2 hours roasting in conventional furnace, and the leaching rates are below 98%. Some preliminary tests were performed on recovery of metals by thermal treated laminar double hydroxide. These materials were introduced into the leaching jet from slag in order to capture the metal anion, which can form solution including chromite, vanadate, and molybdenate. These leach solutions contain known concentrations of chromium, vanadium, and molybdenum. The amount of LDH used is 5 times more to ensure the capture of all anions in solution. The results show that when the content of manganese is high, the capture of chromium is low. And when these metals is low, the capture of chromium is high. It means that these LDH have more affinity with manganese than chromium. Then, to capture these metals, it is necessary first to recover the manganese and then other metals. The optimization of this step is ongoing in the project. Here shows the flow sheet of the IPAS process developed the project, and it consists of the dry low intensity magnetic separation of the EAF slag to recover the iron scrap, which can be recycled in the same furnace. The slag iron scrap free slag first grinded and milled to 125 micrometer. The size fraction of slag obtained then co-grinded with potassium hydroxide and roasted in microwave furnace at temperature between 600 and 800 degrees C for 10 to 15 minutes. The mixture of slag with potassium hydroxide is then leached in water to dissolve the metals contained. After filtration, the residues obtained can be valorized in different applications to recover these metals from the solution. LDH is used. In conclusion, then for characterization, our slide contains more than 3.4% chromium, 48% of iron oxides, more than 1000 ppm vanadium, and 154 ppm molybdenum. And X-ray diffraction reveals the crystalline phases found usually in other different slags like larnite, cerebroborskite, hematite, magnetite, magnemite, and wurtzite, and also compounds carrying chromium like ferrite have also been detected. Also, this element is also dispersed in various other mineral phases. For Mossberg spectroscopy gives different iron balances, and it shows that the slag contains more than 50% of paramagnetic compounds. This modification process allows the leaching of the high proportion, in particular of chromium and molybdenum. For conventional roasting during 2 hours, we have more than 97% chromium and 62% vanadium and 95% molybdenum are leached. For microwave roasting, only 10 to 15 minutes, almost chromium and molybdenum are leached, and only 65% vanadium are leached. The obtained results are promising, seems promising. It's in terms of efficiency. It remains to validate the profitability of the complete process in ongoing project. The authors warning thanks to the financial support of the French National Research Agency, which made this collaboration possible with other partners of the research projects, Armand, Spain, and Lucille. And I would like to thank you for attention and waiting for your questions. Thank you.